The Bob Murphy Show, episode 229.
There's a tidal wave coming. What you gonna do?
Get ready for another episode of The Bob Murphy Show, the podcast promoting free markets, free minds, and grateful souls. It's your source for commentary and interviews conducted by a Christian and economist. Now here's your host, Bob Murphy.
Hey everybody, welcome back to The Bob Murphy Show. What we're doing in this episode is we're taking a little break from the series on Klaus Schwab, partly because I'm still researching his book on COVID and the Great Reset, and also because I want to inject something else here into the mix. A nice sort of a break point, like, now that I've got your attention with Klaus, let's switch to this, because it's something that grabbed me just recently as I've been doing this stuff on Klaus Schwab. I'm not on a first-name basis with the guy yet, but this came across my desk, as it were, and I got to get out of my system. So I got Steve Patterson back on the podcast here. He's been on the show before. I'll link to all this stuff, of course, at bobmurphyshow.com/229. Just to give you a quick background. So here's what's going to happen. I am going to introduce who Steve is, give a little context, explain how the thing that I saw in terms of result from math made me much more sympathetic to Steve's project. And then I'm going to very quickly give you a crash course in what the result is. So that specifically it's called Riemann's Rearrangement Theorem. And there's some other names for it in the math community. And this is the thing, when I saw this, it blew my mind and I realized, oh my gosh, Steve is right. There is corruption at the highest levels of mathematics, right? This goes all the way to the top. Okay, so this actually is connected to the Klaus Schwab series in a loose sense because, well, let me finish that train of thought. And then after I do that, then we will go ahead and jump right into the interview with Steve. But again, I think that context helps. So if you don't care about the context and you just want to dive right into the interview, you're going to skip ahead to the timestamp of approximately 46 minutes and 19 seconds. All right, so if you move your pointer up to that timestamp, then you'll be right before the interview with Steve actually kicks in, okay? So first, let me first give you the bigger picture. So what I'm going to show is, or argue, and Steve is way ahead of me on this, is that just like I think a lot of the listeners of the show already agree that, oh yeah, there's something fundamentally wrong with economics, particularly so-called high-level economics, right? So the standard stuff you might learn in intro classes, that's actually not so bad. But it's when you start going to the advanced stuff, particularly if you go to grad school at a Ivy League institution and you learn what is now touted as like cutting-edge, high-level economics, a lot of you would say this isn't even economics. What the heck? This is nonsense on stilts, and it contradicts good economics. Okay? And whether or not you go that far, you can see at least that that's a plausible case, right? So now they do have economists who doubt free trade, who say that the minimum wage, actually the guys who recently won the Nobel, I think, it was partly their, some of their work on disputing the age-old belief that raising the minimum wage necessarily harms unskilled teenagers and stuff, or reduces employment in that category, right? So a lot of things that used to be standard that, all economists agree on such and such, that even has gone out the window. And so just like you can imagine in psychology or psychiatry, people might argue that, these fields started out okay, but then they took a wrong turn at such and such point in history. That's what Steve Patterson is arguing even happened in mathematics itself, which is supposed to be the most rigorous of fields, right? So I think in terms of the pecking order, most academics agree the smartest people go into physics as opposed to math. And in general, the physicists, particularly, again, at like the top 10 schools and stuff, or research programs, are the smartest people in general. But the mathematicians are very rigorous. Like that's what their claim to fame is. Okay, and so you would think of any human endeavor, intellectual endeavor, where there would not be contradiction would clearly be in math. That's what you would think, right? And yet this result that I stumbled across recently, and how I came across it is I was refereeing an economics journal article, and the author was using this result from mathematics to try to prove something about mainstream economics, to say, hey, they run into this problem because of this result over here. And I had never heard of that result. And I went and looked at it, and I was like, what the heck? I've never heard of this. This is amazing. And it was blowing my mind. And then the more I was looking at it, the more this Riemann rearrangement theorem, the more I was thinking, that doesn't make any sense. Geez. And then I realized this guy, Steve Patterson's right. So what Steve's arguing, he's not saying that arithmetic is wrong. He's saying, though, that, and again, this is sort of analogous. If you're a fan of the Austrian school, you can say, oh, yeah, Bastiat's great. Adam Smith is okay. But really where economics took a horrible turn was in the 20th century with, Keynesianism and just the mathematization of it, where the economists were trying to ape the physicists and so forth. And that much of what's come out of the economics profession post-1950 has been garbage. And that's not a surprise that central banks keep crashing the world into the Great Depressions and such, right? That if its foundations rest on quicksand, it's not surprising that the practice is bad too. And so Steve is arguing that something similar happened in mathematics in the 1800s at some point. And when he is on here for the interview, I'll let him explain his own position with more detail. But that's what he's arguing. In particular, the introduction of infinite sets and the idea of a completed infinity being something that we can use in math. That's the thing where Steve said that crept in and that was a mistake. And so, again, what I'm going to do here in this little intro is show you a result from mathematics that it's standard stuff. My brother got a master's in math, and I asked him about it, and he said that, yeah, you only need stuff that you would have learned in a regular calculus sequence to see the proof, but he actually hadn't seen it. Like, in other words, he didn't know of this result until he went to grad school. And with a lot of this stuff, it's kind of, that's the pattern you see, that somebody gets into an area and the introductory stuff kind of shows, like, this is what made our field famous, and this is why humans use this, and some age-old results. And then the deeper you get into it, you sort of like ascend the hierarchy of the priesthood, and then at some point you start learning stuff that's just nonsense. But yet at that point you're so invested in it, and you've, mastered the jargon and the technicalities, and you're special because you're one of the few people who know how to converse in this language with your fellow practitioners of this discipline, or this alchemy, if you will, that at that point you're already in it. Okay, and so this lines up. And what's funny is the email I sent to my brother, the subject line, I actually said, how come no one told me about this before? Because I was actually like scandalized, like in my mind, and that's why I'm doing this episode and going through the trouble here of expressing this to you folks, is if you fully comprehend what this guy Riemann discovered, or proved, I should say, because some earlier people had discovered examples of it, and he just kind of gave a generalized proof to show, how big an issue this was. This isn't like, oh, wow, math's kind of quirky, isn't it? I didn't expect that. It's more like, in my mind, whoa, we took a wrong turn somewhere. This should not be happening. If this is popping out of our process is wrong. All right, so that's why I think this is such a big deal. Okay, to give another analogy, it's sort of like arrows and possibility theorem, which I've done an episode on. I'll put links, of course, to this stuff, folks. So again, this is bobmurphyshow.com/229. Let's see, so I'll put a link to the previous Steve Patterson. I'm jotting notes. And I'll put a link to my episode on Arrow's theorem. I also, if you guys remember early on, one of the first episodes I did with this podcast was I explained Gödel's incompleteness theorem, or the plural, because I think I've touched on the other ones too. All right, so let me just say that in case some people listen to this are like, okay, Bob, you're an economist, you're not a mathematician, you're out of your league, Donnie. I don't think so. I think I understand Riemann's rearrangement theorem enough to state it and to know what it, quote, means. And I'm saying something's not right here. And you cannot just take the word of the people who are in the field. Because again, some of the people who are least likely to say, oh yeah, our entire discipline took a wrong turn in the late 1800s are the people now who are invested in it. All right? Not because they're evil and sitting back and twirling their mustaches, but just because, like I say, once you get that deep into it, what are you going to say? Oh, I just wasted 4 years of my life in a grad program and I should go do something else. You're not going to be likely to do that. You're going to just say, oh, wow, this stuff is even more complex and weird than I thought. Okay. So I think I've given enough, like I say, so I came across this, I was refereeing an article, I stumbled across this result, I checked with some people, I did some more research, and I think I am on solid enough ground to tell you folks what the result is and hopefully convey to you why it's disturbing at the very least. And then, like I said, I reached out to Steve and said, hey, were you aware of this result? And he wasn't. And he's like, wow, that's a great example of the kind of thing I'm worried about. All right. So Steve was already smelling a rat before this. And let me also mention, too, just in terms of showing you folks, it's not like I was pining for this outcome, right? And like, oh, yeah, I just want to see conspiracies everywhere. No, I used to kind of gently mock Steve, things like he was saying how so-called imaginary numbers were goofy. And in fairness, that's why they call them imaginary, right? That's not just a frivolous term. They meant in contrast to real numbers, right? So those terms, they picked those labels for a reason, the mathematicians. And so like so-called imaginary numbers are all predicated on the basic building block of I, which is defined as the square root of -1. Okay, so if you think about it, that doesn't make sense, right? Because a negative number times a negative number is a positive number. Okay, so when you say, what's the square root of -1, what you're saying is what number multiplied by itself, or squared, yields -1, right? So the square root of 9, it's 3 or it's -3, right? Because -3 squared turns into 9 or 3 squared turns into 9. So that's why the square root of 9 is plus or minus 3, right? Just two answers. Okay, but to say the square root of -1, you say, okay, what number multiplied by itself or raised to the second power yields -1? And the answer is nothing, because the way you get a negative number is you got to multiply a positive times a negative. If you multiply a positive times a positive, or if you multiply a negative times a negative, the answer is positive. So there's no way to actually, with quote, real numbers, get something such that the square root of -1 makes sense. Okay. So what they do, though, with imaginary number, and then it's called a complex plane, where you have imaginary numbers and then you add real numbers to them, is they just say, well, okay, but let's just go with me on this one. Let's assume, for the sake of argument, that the square root of -1 means something, and we'll call it I, and then let's build a math, on that. We'll use all the other rules from math that we have with the real numbers, and we'll just apply it in this different realm, this different plane called the complex plane, where one of the dimensions is I, okay? And then there's results there, and it just so happens that the math in that area is very useful in electromagnetism, okay? So for people in the real world who want to make circuits and stuff, you use physics equations, theories in physics to explain electrons and blah, 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 voltage and stuff, and I is involved in that, or, the imaginary numbers, complex numbers. Why? Who knows? God has a sense of humor or whatever. God wants to just keep us on our toes. Who knows? Keep us humble. When we think we figured things out, he throws a curveball. I don't know. But the point is, it's useful. And so I used to make fun of Steve when he would say things like, oh, imaginary numbers don't make any sense. It's dumb. And I would point out, well, you just threw out circuit boards and stuff. Okay. So the reason I'm sharing this is I want to show you, like, I changed my mind on this. All right. And so that's why now I'm so passionate about it, is because I realized I was making the mistakes. So now when Steve says the mathematicians and the fans of higher math, not the practitioners, but like, how some people are like really fans of Darwinian evolution, even though they're not biologists, but they're just really into it and they like to argue it on the internet. So Steve was saying, when he started challenging some of this stuff, and this, I'm not putting words in his mouth, he says literally the dogmatism he encountered was more vociferous and vocal than when he argues theology with, evangelical Christians. Okay, and I believe him now. And like I say, I can remember when I'd like to think a jerk about it, but I would lightly tease him. And there was the assumption too that, Steve, you probably just really don't understand these proofs the way, like, I could literally get up in front of an undergrad class and prove some of this stuff. I bet you couldn't, Steve, because you don't really get it like I do, right? There was that element of arrogance too. And like, hey, I'm part of this secret club, these ninth level Masonic cult or something. And you don't really get it. You can't speak our language, and I'm in communion with the ancient Babylonians, right? Okay, so there you go. That's enough of the background, the sort of sociological context of this. And you can see, this is something that's plaguing humans. You can see it in all these other fields. I personally, of course, know it quite well in economics. Right? The people running central banks are not stupid, but they're fools. Right? They are way too overconfident in their models and whatever, and they tell themselves lies, and then look at the results. Okay, and so I've also seen it in, I guess, cosmology would be the field. I'm sitting in the planetarium with my kid, and Neil deGrasse Tyson is the narrator, and he starts going on about this stuff, and okay, look at these quasars, oh, that's cool. And then he says something like, in fact, we now know that up to 97% of the universe consists of dark matter and dark energy. All right, it might not be 97, but it was up there, it was above 90%. And that's when my spidey sense went off. And I went, you know what? If they're saying 90+% of the universe is dark, that means their models are wrong. That's what that means. It doesn't mean that, it turns out most of what we think is out there we can't observe. No, it means their models are wrong. And that's why their earlier predictions weren't lining up. All right. So, it's one thing if you see some stars circling something that you can't see anything in there. And they say, you know what, maybe there's a black hole right there. That would explain why these stars are moving around something, even though we don't see anything from right there. Okay, fine. But when you end up saying 90+% of the whole universe is stuff that we can't observe, like I say, my hunch is no, that means your models are fundamentally flawed and you need to find a different paradigm. Okay, so likewise, now I'm saying what I had thought mathematics was free from that because I thought it was so logical and rigorous that fallacies couldn't creep in there because they would be identified. They would stick out like a sore thumb. And yet, to me, it seems like there's something that I would say it's a contradiction. And hence, the mathematicians should have realized, okay, we made a false step here. They don't think that in general. Okay, so with all that prelude, let me go ahead and start giving you what you need to understand Riemann's result. Okay, so first of all, let's talk about a finite series, or a sum, I should say. Okay, so just think of this. 1 + 2 + 3 + 4 + 5. What does that equal? It equals 15, right? You can do it manually in your head, or you can use the trick. I think Gauss developed this trick when he was like a little kid in school, that you can go to the halfway point, which is 3, and then multiply it by the number of digits, which is 5, right? Because you can take 2 away from the 5 and move it over to the 1. So it's a 3 on the left and a 3 on the right. And then take 1 away from the 4 and move it over to the 2. So that's a 3 and then a 3, right? So if you want to do 1 + 2 + 3 + 4, all the way up to +100, or you can do 101, you do the same trick. You find the mid number, and then that's what they're all going to be on average, and then multiply it by the total number of numbers, and that's how you get the sum really fast. Okay, so there's an anecdote that Gauss, the teacher, gave the kids some busy work, and said, okay, everybody take out your little slates and, and your chalk or whatever. And I don't know if they used chalk or coal, who the heck knows, but they did something back then. They didn't have iPads, that's for sure. Tell me the sum of 1 + 2 + 3 + 100. And so all the kids are sitting there, and the teacher's whatever, doing some opium or whatever they do. And little Gauss is just looking out the window, thinking about stuff. And then he just writes down the answer on a piece of paper and goes up and hands to the teacher, and he's right. And the teacher's astonished, like, how'd you do that? And he said, well, because I just pictured it in my head. And I realized I could, for each number going left and right, I could just take some from the right one and bring it over so that, it would just be the same number added 100 times. And so then it was just 100 times that, right? And so specifically, just so so 1 up to 100, the midpoint is actually, because there's an even number. So there's not one number that's the midpoint. So it's like in between. So what's 1 up through 50 is the first 50, right? And then 51 up to 100 is the second 50. So the midpoint is actually 50.5, right? Because if you're picturing it in your head, 1 + 2 + 3, all the way, okay? And so then he realized, okay, so on average they're 50.5, and then there's 100 of them. So it's 5,050 is the sum. And so he just did that, just picturing it in his head for a few seconds, and then went up and said 5,050. So if you sit there and manually add them up and did it right and didn't make a mistake, you'd get the same number. But, he did it very elegantly. And apparently, as the anecdote goes, the teacher was like, go back to your desk and do it the right way. Which, who knows whether that actually happened, but that's hilarious if that's what happened. Welcome to the world, Gauss. Okay, so anyway, back to what I was saying. That was sort of just a tangent that wasn't necessary for this episode. So 1 plus 2 plus 3 plus 4 plus 5, you can, do it manually, or you can just say, 3 is the midpoint and 3 times 5 is 15, right? So that's what it equals. So now I want to say to you, if you agree that 1 plus 2 plus 3 plus 4 plus 5 equals 15, what if I rearranged those numbers? Like, what about 1 plus 3 plus 2 plus 5 plus 4? So it's the same numbers, they're just in a different order. What does that equal? And I think you'd agree it's 15, right? So you can do it manually and check it, but also just the nature of how addition works. What is that, the commutative property? You know that the order shouldn't matter. When you rearrange the order of stuff you're adding together, that doesn't change what the sum is. Okay, so what Riemann generally, again, it's not that he discovered this per se. Other people had discovered instances of it, and then Riemann kind of came up with a general theorem to show the big picture of what was happening. What Riemann discovered was if you have infinite sums, right, so series that go on forever, like sequences of numbers that you're adding together, and under certain conditions, even though in one particular order the numbers add up, well, let me go ahead and state it. If what you have is an infinite series and it consists of positive and negative numbers, and if you just looked at the positive numbers, it would go to infinity, and if you just looked at the negative numbers, it would go to negative infinity if you added them up. But if you combine them so that they sum to a finite number, for that kind of a series, which is called conditionally convergent series, you can rearrange its terms and make it add up to any number you want. Okay? So it's not just that by rearranging it, you can come up with a different number. It's that you can tell me ahead of time, what do you want this series to add up to? And I can tell you the number, the target, and I can rearrange the terms in that series such that they add up to that number. Or I can say, rearrange the terms in such a way that they don't add up to a finite number, that the whole thing added together goes to infinity. Okay? And so that would be like saying, in a finite context, that would be like saying 1 plus 2 plus 3 plus 4 plus 5 equals 15. If I then now you tell me, what do you want those to add up to? And then I can rearrange them to add up to that number. Right? So it's not just that if you rearranged it in a certain way, it happens to be a different number. Imagine if I could make that sum be any number you wanted just by rearranging the terms a certain way. So you would realize that would be crazy, right? That no matter how you rearrange those terms, it adds up to 15. So it's one number, let alone an infinite number, meaning that I can make it add up to anything I want. Okay, so again, let me just state it again in words. What Riemann discovered was if you have an infinite series with the following properties, so it consists of positive and negative numbers, and if you just looked at the positive ones and added them together, it wouldn't be finite. It would go to infinity. If you just looked at the negative numbers and added them together, they would go to negative infinity. But when you combine them in the same sequence or series and you add them up that way, they converge to a finite number. All right. And then what the term for that type of a thing is called a conditionally convergent series. For that thing, for anything that has those properties, Riemann said, you tell me what you want that to add up to, and then I will show you how to rearrange the terms in that series, right? So he's not adding in different numbers. He's taking that series as it is and then just rearranging the terms, the order in which you add the terms up. That's all he's doing. He's not putting in new numbers. He's not pulling up. He's not removing numbers from it. He's just taking the existing set of those numbers that happen to be in a particular order originally that added up to some finite number. And then he's saying, what do you want it to add up to? You tell me. You tell him ahead of time. And he says, okay, here's how you would get to that number. And I can just rearrange these terms to give, here's the process, the procedure you would use, the algorithm to take that sequence, that infinitely long sequence of numbers and rearrange them in such a way that when you add them up, the way, how do mathematicians add up an infinite string of numbers? Well, there's a way, and we'll talk about that in a minute. When you add them up, it yields that number you just told me. Or if you say, you know what, can you rearrange this same sequence of numbers, just change the order in which we add them up, such that when you go to do it, you say, you know what, this doesn't converge to a finite number. It just gets bigger and bigger without limit. He said, we could do that too. You tell me, what do you want? All right, so that's what his result is. And I'm claiming, if you let that sink in, what he's saying. To me, that shows there's something crazy going on with the way mathematicians handle infinite series, or adding an infinite series, and the definitions they use to say, what does it mean to say this is the sum of an infinite number of numbers, okay? Or a string of numbers that has infinitely many elements. So this dovetails with the kind of stuff Steve Patterson's talking about. That's one of his points, that when mathematicians started incorporating notions of infinity and started doing arithmetical operations on sets that contained an infinite number of elements, as if, it's like finite, it's like doing stuff on a finite number, except we're just going to let it go on forever. And what would it look like if, in principle, we just did this same procedure forever, and then it yields a result? And Steve is saying something's goofy going on there because it pops out absurdities. And so normally in math, this is me talking now, there's things called a proof by contradiction. That if you want to prove something, one way of doing it, like you want to prove X, let's say whatever X is, some statement, some condition. One way of doing it is to say, let's assume not X, and then use the standard rules of logical deduction. And then if we can generate a contradiction, that means not X must not be true, because you shouldn't be able to generate a contradiction in math. And so then you say, okay, because we've just shown if we assume not X, it yields a contradiction, therefore we can conclude X must be true. Because if we assume not X, our heads explode, and we don't want that to happen. Okay? And so I'm saying here, likewise, it seems to me mathematicians are admitting, okay, these procedures we use, or these definitions for what does it mean to add up an infinite sequence of numbers or infinite series and come up with a sum, to say that is what we mean by saying this is the answer for adding up this infinite number of members of this set, allows you to say, for certain types of these animals, when you just rearrange the order of their elements and add them up again, you get a different number. The answer is different. And again, I want to stress here, it's not that it's infinity, right? Because there's weird stuff that goes on. Like you might say, let me give you an example. I could say 1 plus 2 plus 3 plus 4 plus 5, forever. What does that equal? Well, it doesn't equal anything. You could say it's boundless. You can loosely speaking say it equals infinity. Technically, that's ungrammatical. You would just say the limit of that is boundless. Okay? Loosely speaking, you could say it equals infinity. Okay. Now, what if I double each one? What if I say, what's 2 plus 4 plus 8 plus 16? Or wait, no, I'm doing that wrong. 2 plus 4 plus 6 plus 8, and so forth, right? I'm not doubling each element, I'm doubling the original thing, right? You could do that. You might want to say, that equals 2 times infinity, right? Because each element is twice as big as the original one. So if the original one adds up to infinity, then the second one should add up to double infinity. But infinity is infinity. What's 2 times infinity? It's just infinity, right? So you might think that that's the kind of semantic trick that we're playing here. Like, oh yeah, Bob, when you add up infinite stuff, weird things. And that's not what's going on here. So I want to be clear. What I'm saying, what Riemann found, is much weirder than that. Because these series do have an infinite number of elements, but it's not that they, quote, add up to infinity. That's not what I'm saying. What I'm saying is you can have a series that the standard way that mathematicians talk about what does it mean to add these numbers up in this particular order, it comes up with a finite number. It comes up with a 0 or logarithm of 2 or whatever. And then they say, okay, so it's not infinite, it's not infinity. The things add up to a finite number. And then they're just saying you rearrange the order of those elements and add them up again using the same definition that mathematicians use for what does it mean to add up a list of infinite numbers or an infinitely long list. And there's a different answer that's also finite. Okay, so that's weird. And I'll leave it at that in terms of the stating what it is. Okay, now let me just give you a little bit more. We'll just go for a few more minutes here just to warm you up so you can kind of see a little bit more concretely how this stuff works. Okay, so what about if I just start adding 1 plus 2 plus 3 plus 4 plus 5 plus 6 forever? Clearly, you would say that diverges. That's what the language they would use. Loosely speaking, you could say it equals infinity, but again, that's not really grammatical. You'd say it tends toward infinity, or you could say any finite number you pick, no matter how big, I can continue that sum, I can continue that series out, and eventually I will be bigger than that number. So you could say, well, what about 60 quadrillion, quadrillion, quadrillion? If I continue that 1 plus 2 plus 3 plus 4 long enough, and I could figure it out for you if you wanted, at some point I would have, even with just the partial sum, not taking the whole series, but just some of it, I would have exceeded 60 quadrillion, 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 or whatever number I said. And I could do that for any finite number you pick. I can always just keep going on that plus n plus 1 plus n plus 2, and eventually I will surpass that number, that ceiling that you picked. So that's why you would say that series diverges, right? It does not converge to a finite sum. Okay. What about 1 plus 1 plus 1 plus 1 plus 1 forever? Similar thing, right? So notice in the first one, each element gets arbitrarily big. So let alone, adding up that plus all the previous elements. But even if the elements themselves just are finite numbers, well, even if they stay below some threshold, so like 1 plus 1 plus 1 plus 1 plus 1 never gets bigger than 1, but you can see adding that up forever, it diverges also. Okay? And now, try a different one. What about this? 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus forever, right? So each time I take 1 over, and then it keeps doubling the denominator. That adds up to 1, the way mathematicians define these concepts. Okay, so strictly speaking, you'd say the limit of that series as n goes to infinity is 1. And that's what it means, loosely speaking, to say 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 forever equals 1. And it's really easy for that one. The reason mathematicians use that a lot to get these concepts across is because it's really easy to picture it geometrically. Just imagine a square in your mind, and then at first, and you're moving from left to right. So at first you shade in the left half of the square, and that's 1/2. You've just filled in 1/2 of the area of that square. Now you've got your picture in a square where the left half is shaded and the right half is still like open. And now, so that was the adding the 1/2. Now you're going to add the 1/4. And so that's half of the remaining area, right? Because it's 1/2 of 1/2 is 1/4. So of that remaining empty space on the right half of the original square that you just filled in half, again, now cut that in half and fill in the left half of that part. And so now you've just got the rightmost 1/4 is still open, and the left 3/4 is now shaded in. And now you're going to color in 1/8. And that's, again, half of what's remaining. So if you're thinking of it that way, you keep doing strips that are always 1/2 of the remaining area of this square that's still needing to be shaded in or colored in. And you could just keep doing that forever. With each step, you just keep filling in 1/2 of the remaining empty space. And so you can see how if you did that forever, what does that mean? If you did the infinite number of steps, eventually, so you got to be precise here. It's not that you would ever actually fill in the full square, because you would never complete the process. But you can make the remaining empty space arbitrarily small. And you'd say the limit as n goes to infinity of doing those steps, one at a time discretely, is that the total sum of how much of that square had you colored in would equal 1, or 100% of the square. Or you could look at it the other way and say at any given time or any position in that sequence, how much of the square remains unshaded, and that thing would shrink to 0 eventually. That would be the limit, to be more precise. Okay, so there you can understand the sense in which, if you pictured that, the sense in which mathematicians think that 1/2 plus 1/4 plus 1/8 plus 1/16 plus blah, 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 it converges to 1. That's the precise statement. And then loosely speaking, you say it adds up to 1. That's what they mean. Okay? Now, let me throw another curveball at you. You might think, oh, okay. So what happened there was each extra term that we added on, right? So first it was 1/2, then it was 1/4, then it was 1/8. Notice that those things get really small and they go to 0, right? The bigger it gets, it gets to be 1 over 1,024, 1 over 2,056, that thing gets really, really small. And so it kind of makes sense that as you keep adding constantly shrinking things to the number, the total, the sum of all those things added up, sort of converges to a finite number. Like there's a ceiling above which it can never rise. And that's what it means to say it converges to a finite number. So that's a necessary but an insufficient condition for the thing to if it's all positive numbers, to converge. Okay, so, and what I mean by that is you can come up with examples where the numbers you keep adding do shrink to zero, but still the sum itself has no bound. And the most famous one is what's called a harmonic series. So that's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 forever. That thing, even though the individual terms get arbitrarily small, right? Eventually it's like you're doing plus 1/17 trillion, which is a very small number. Even though each little thing that you add to it gets microscopically small, nonetheless, that whole sum diverges. Okay, and I'm not going to prove it. There's a lot of elegant proofs. You want to look this stuff up. I'll obviously put some links, folks, at bobmurphyshow.com/229 for some of this pure math stuff on Wikipedia and other places if you want to see it spelled out more formally. But what it means to say it diverges is you give me any number you want, no matter how big, 60 quadrillion, and I can show you if you just keep doing plus 1/6, plus 1/7, plus 1/8, plus 1/9, at some point, that sum will be bigger than the 60 quadrillion or whatever number I said. Even though you might think that, no, that doesn't sound right because they're shrinking. Well, you've still got an infinite number to add. And, loosely speaking, intuitively, if you want to say, well, the reason those are different is because when it kept getting cut in half, it was like shrinking faster than when you're just, making it go down by n as opposed to 2 to the n in the denominator of each term, right? So the plus 1/4, plus 1/8, plus 1/16, those shrink faster than the plus 1/2, plus 1/3, plus 1/4, if you think about it. And so, if that's the intuition you need to kind of help make that make sense to you, fair enough. Okay. But again, whether it makes sense to you or not, the way mathematicians use these results or define these concepts is that 1/2 plus 1/4 plus 1/8 plus 1/16, that adds up to 1. Whereas 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, blah, 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 forever, that doesn't add up to any finite number. That gets arbitrarily large. And so that you can say that diverges. Okay, so now we got some of those concepts under our belt. And this is all standard stuff you would learn in a, calc sequence. Okay, so now that you got that, again, let me restate now what Riemann's rearrangement theorem found. So if you have a series that consists of positive and negative numbers, and if you just looked at the positive numbers, they would diverge. There would be no upper bound on it. You would add them up and they could always exceed any finite number. And then you also had negative numbers that if you added them up, they would diverge the other way, that there's no lower bound. You could pick negative quadrillion, 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 and yet you keep adding more terms of the negative ones of this original series. Eventually, it's going to be smaller than that. But when you add them together, when you combine those two different things into a particular sequence, if that added up converges, well, the label for that is called, it's a conditionally convergent series. And what Riemann found was, or proved, is that for such a series, you tell me what number you want it to add up to, and I can take that existing series and just rearrange its terms and make it add up to that number. Or if you want, you can say, I want it to diverge, the originals, the series itself, not just the positive and negative components, but the whole thing we added together, positive and negative mixed up, or, put into together with each other. I want them, the way mathematicians add up an infinitely long series, to not have an upper bound. I want to go to positive infinity. You can do that too. All right, and that's what he found. So let me now just give you a particular example just to make sure you understand how this stuff works. Okay, so consider this infinite series. 1 minus 1 plus 1/2 minus 1/2 plus 1/3 minus 1/3 plus 1/4 minus 1/4 forever. Okay, so again, I'll say you start with positive 1, then minus 1. Positive 1/2, minus 1/2. positive 1/3, minus 1/3. You see, you just keep doing that forever. So that series, the limit of that, as you do the partial sum, you take any finite number of elements in that series and add them up, and it'll yield some number, and then you take the limit of that as n goes to infinity, that sums to 0. Okay, and so notice, because every other term, the thing sums to 0, and then if you think about it, like the amount that it exceeds it one way or the other gets smaller and smaller, right? So you just do the first term, it's 1. Then you add the second term, which is minus 1. Now the partial sum goes to 0, right? Because it's 1 minus 1 is 0. But then if you do the third one, it's 1/2. So now it bumps up again. But then if you do the fourth one, include that, now it's minus 1/2, so it's back down to 0. So notice you keep doing that. The partial sums go like 1, 0, 1/2, 0, 1/4, 0. Or sorry, 1/3, 0, 1/4, 0, 1/5, 0, as you keep adding more and more terms. And so you'll notice that partial sum gets smaller and smaller. Well, it's alternating. It's either 0 or the other thing. And so the limit of that goes to 0. And so that's the sense in which that original series converges to 0. Okay, but notice it's conditionally convergent, right? So if you just looked at the positive elements of that, it's 1 plus 1/2 plus 1/3 plus 1/4, right? And we already argued, I didn't prove it to you, but I'm telling you that's a harmonic series, and that diverges positively. It goes to positive infinity, and then likewise, that thing with just negative numbers in front of it diverges to negative infinity. Okay, but yet if you arrange them in that particular order, like I said, where you go 1 minus 1 plus 1/2 minus 1/2 plus 1/3 minus 1/3, it's pretty intuitive to see that thing, quote, adds up to 0. Okay? So now here's what's weird. Up till now, things might have been fine for you. You might have said, okay, yeah, that thing adds up to 0, and I can see how that works. Sure. But now, you probably would have thought, if that thing adds up to 0, if I rearrange the terms, it should still add up to 0. And yet, that's not the case. So here's a particular way to rearrange it. We're going to take that original list of numbers, and there's going to be the same numbers constituting this new list. It's just we're going to change the order of them. So specifically, what we're going to do is we're going to take 2 positive numbers at a time and then 1 negative one. Okay, so we're going to take that original list and just pull out the first 2 positive numbers, then pull out a negative number, then pull out the next 2 positive numbers, then pull out a negative number, and so on, and add that thing up. And notice it's the same set of numbers, constituents, elements. It's just the order is different. And you say, well, how do you know it's the same number? Because every number in that second set that I construct came from the original one. Like there's a 1-to-1 correspondence. That's like a more formal way of saying it. So every number that was in the original list, we know is going to end up in the new list. And every number in the new list, we know had a corresponding member in the first list. So it's the same set of numbers defined by its elements. It's just the order in which we're adding them is different. Okay, and so specifically, in case you're getting lost, this is what the new sequence looks like, or series looks like. It's 1 plus 1/2 minus 1, plus 1/3 plus 1/4 minus 1/2, plus 1/5 plus 1/6 minus 1/3, and so on forever. So again, that's the same set of numbers in the first list. It's just we're changing the order. Instead of going 1 minus 1 plus 1/2 minus 1/2 plus 1, we're just taking the first 2 positives. So that's why it's 1 plus 1/2. Then the first negative, which is -1. Then the next 2 positive, which is plus 1/3 plus 1/4. Then the next negative, which is -1/2, and so on. Right? So it's the same. Again, every number that's in that new list or series that I'm listing was in the first one. And going the other way, every number in that first list is in that second one. And notice there's no duplication. It's a 1-to-1 correspondence. Okay. So now, if I just, without context, told you, and you had been trained in math to say, hey, the series 1 plus 1/2 minus 1 plus 1/3 plus 1/4 minus 1/2 plus which is that second one we constructed. What is that? You'd say, well, If you just looked at the positive numbers, it diverges to positive infinity. If you just looked at the negative elements, it diverges to negative infinity. But if you add them up all together in the particular sequence or order that you just listed them in, it actually conditionally converges to the natural log of 2, which you write out as ln2. Okay, so obviously, me just talking to you guys, I'm not going to totally be able to show you that, but that's what it converges to. The natural log of 2, which is not the same thing as 0. The 0 and the natural logarithm of 2 are different numbers. Okay, so that's just one example where we're saying, and so what Riemann showed is this isn't just a rare thing. For any conditionally convergent series, you tell me what number you want it to add up to, and I'll show you a way that you can rearrange the elements to add up to that number. All right, and again, that would be like, in a finite context, that would be like saying 1 plus 2 plus 3 plus 4 plus 5 equals 15, but 2 plus 3 plus 1 plus 5 plus 4 equals 7. And that would be crazy. And yet, that's what happens with conditionally convergent series. Okay, so I will stop there. That's enough of a math primer. And we will now get into my interview with Steve Patterson to not so much talk about this particular result, but just step back and talk about what the heck happened in mathematics more generally. And then also, why do we care? So what about this stuff? Well, Steve, welcome back to the Bob Murphy Show.
Hey, thanks for having me.
So let me just give a very quick introduction to set the context, because I did tell people in the formal introduction of this that, hey, if you don't want to hear all this, just jump ahead. And so in case someone did do that, and I tricked them, they need to know just a little bit of the context. So you, for a while, have been going around looking at all these different fields of human inquiry, and have thought a lot of these fields started out strong, and then they took a wrong turn at some point, and it ended up like corrupting the discipline, if that's the right word. And it takes an outsider, because the people who are enmeshed in it, they're not going to see it. Right. So it takes someone, and also like you gain from having seen this type of thing in other areas where they think, oh no, that's not happened here.
Yep.
So, I was very sympathetic to your project, but I always thought, come on, when it comes to math, give me a break, Steve. That's the most rigorous thing around.
Of course.
They're not, missing. They know exactly what they're doing. It's extremely rigorous, and come on, you're in over your head there. And also too, it's sort of like, I really get it, Steve. You must not get it the way I get it. There is that element involved. Uh-huh. And also too, like, look, it took me so long to learn their vocabulary and to be able to prove this, Gödel's theorem or whatever. And so, don't tell me it's not important, because look at how much time I just wasted learning this stuff. So there's all that. So what changed my mind, but in this episode, I'm going to adopt a posture of like pushing you, is I came across this thing called Riemann's Rearrangement Theorem, and I'll just very intuitively just say what it showed folks. And then again, you can back up if I've intrigued you and you want to go listen. And I really spell it out more carefully in the longer intro of this episode. But something like in a finite context, 1 plus 2 plus 3 plus 4 plus 5 equals 15. And if you rearrange the order of that, 1 plus 3 plus 4 plus 2, I missed a 5 in there, then it still equals 15. I guess that's what the commutative property, the order in which you add things up shouldn't affect what the total is. And yet what Riemann showed is for certain types of infinitely long series that do sum to a finite number, the way mathematicians define that, right? So we're not just saying, oh, when things go to infinity, weird stuff. That's not what we're saying, or that's not what Riemann's saying. He's saying that these series that have an infinite number of elements in them, even though they converge to a finite sum. So you can say, oh yeah, this thing added up forever tends to 0 or tends to the logarithm of 2, right? So it converges to a finite sum if you rearrange the order of those elements, but it's the same elements. You're not changing the set of what's being added up. It changes the number, changes what it adds up to. And in fact, you can make it add up to anything you want. And Riemann gives an algorithm by which you can just rearrange those elements in that infinitely long set of numbers to make them add up to whatever number you want. And so I thought, okay, that is weird, and I don't know what else you would need to see that something screwy is going on when the way mathematicians define what does it mean to say there's a sum of an infinitely long series of numbers. And so then I sent it to Steve, and he said, yep, see, what'd I tell you, Bob? And then also you said something funny. I'm not going to get the exact wording right, but you said something like, I encourage you to go ask mathematicians who are well-trained and whose integrity you respect to talk about this. And if you do, you will realize it's all built on a house of cards. Or you said something like that. Like you took me in a way I wasn't expecting. And so, and I haven't done that yet. But you're right. I did blast it out on Twitter, and not that it was necessarily math PhDs who answered me, but you're right. I got the, oh, you just don't understand how this stuff works, Bob. And I was like, I actually think I could teach it in an undergrad class. I understand what they're saying. But okay, so I'll stop there and now turn over to you. So what's going on with math? What happened there?
So, from what I can tell, there was foundational crises in multiple disciplines around the turn of the 20th century. So let's say from the period of 1880, I'm going to say to 1950, there were crises in mathematics, there were crises in psychology, there were crises in philosophy, and there were crises in physics. So not to go into physics, but if you want another rabbit hole to go down, what was the dominant interpretation in quantum physics over the 20th century is called the Copenhagen Interpretation. And it's utterly preposterous. It's the claim that essentially there is no, reality is not in a state prior to observation. The reason they give for this is convoluted, but it ultimately, I think, comes from a confusion about the philosophy of mathematics. That is to say, they could only come up with formulas that were making accurate predictions in the aggregate. It could not make specific predictions. In other words, 50% of the time, the particle would go this way, 50% of the time it would go that way. And they said, therefore, reality isn't in a state. It's actually in a probability cloud, whatever that is. And when you measure, then it takes a particular state. Okay, that's a nonsensical idea. But it comes from the same general time period. So what was happening in mathematics is this is the story that I'm going to tell. This is the story that you'd also hear from Dr. Norman Weilberger, who's an absolute genius when it comes to pure mathematics and the history of mathematics. I encourage everybody to check out his work if you're curious about this. The brief story I would tell is that mathematics, loosely speaking, in the West, was built on Euclidean geometry for like 2,000 years. People thought that Euclidean geometry was the only true geometry out there. In fact, there was a lot of people who said this is an a priori true. Like it is necessarily the case that Euclidean geometry is true. People like, you could say Immanuel Kant made this argument. And then like in the preface to the Critique of Pure Reason, he's trying to investigate the category of a priori true knowledge about the world. One example he gives is Euclidean geometry. Okay. So what happened was around the late 1800s, people started discovering non-Euclidean geometries. And they said, well, hang on a second. If there are consistent non-Euclidean geometries, what is actually the foundations of math? The foundation we thought was solid for 2,000 years is not actually so solid. Now, we could have a discussion about some problems with the non-Euclidean geometries at the time, because they said, what if space is curved? And then you get into some difficult questions here. Anyway, there was a foundational crisis. People said, okay, well, maybe math doesn't rest on geometry. Maybe math is a subset of logic. So there was one school of thought, the logicists, that said math ultimately comes from logic. I actually think they were right, but they had some bad philosophical assumptions. And we could talk about some academic logicists here. There was another school of thought that said actually math is all convention. It's all intuition. There's no truth. It's all up in the air. Those were the intuitionists. They took things to an extreme. They got some things right. And then there was another school that wound up winning in the end, which is the formalists, which essentially said, look, math is not, there's not truth and meaning in math. All math is you write down a bunch of symbols, and you write down the rules for manipulating those symbols. You don't ask philosophical questions about meaning. And then it's just a question of mechanically moving your symbols around on a piece of paper until you get some output that you say is meaningful, and maybe it's actually meaningful in the real world. But there's no fundamental connection that we know between math and truth and reality. And part of the reason they did this is because they ran into philosophical problems that they couldn't resolve. In my language, I would say they ran into a bunch of contradictions. And so instead of saying, oh, we have to do more work here, they said, listen, don't ask philosophical questions about the philosophy of math, about the meaning of mathematics. These questions were not... And something actually happened in physics too, again, not to go into a rabbit hole here, but part of the spirit, the ethos of the Copenhagen interpretation was this phrase, captured in the phrase, just shut up and calculate. Because a bunch of physics students would say, hang on, you're claiming reality is in a mutually exclusive state. I don't really understand what this means. And they say, shut up and calculate. The math works.
Right,
don't ask the
right.
philosophical questions. So that's how I would try to answer the question, what happened? And we have not resolved these foundational crises. So we're still in a period in math and physics, I would say, but in mathematics where the foundations have been undermined. People said, don't worry too much about truth. And then we've had a bunch of academics who think that they can just assert any old axiom and build new mathematical theories on top of these axioms that aren't true, or they result in various logical contradictions. The one you brought up, there's also the Tarsky paradox. There are even still problems with Zeno's paradoxes that haven't been resolved correctly. So that's the big picture explanation, I think, to explain the current situation.
Okay, let me just mention, Steve, if we end up using your good audio, it won't matter, but you're getting all into it, and I think your mic keeps bouncing on your clothes. Like
really?
It keeps like doing like as if you're doing some kind of percussion instrument as you're talking. Okay. Just so you're aware. And for the folks at home, say, Bob, you're insane. It's probably because Steve also has a good audio on a different mic that we may end up using. Okay, so that's good. And it's also in. I know exactly what you mean. This idea that, hey, don't ask me what does this mean. It is, here's the equations. And that happened to me when I was in grad school. Mm-hmm. It was a game theory class, and unfortunately, I can't remember what the issue. It was something like the prisoner's dilemma, but it was more sophisticated than that because this was like a second level, like for people who majored in theory, and so I mean, this was way deeper than the prisoner. But it was some issue where it was a really hard thing, like this problem to resolve, and I just kept saying to the guy, yeah, but is that the resolution of this? Like and he just said, all I'm telling you is this constitutes a subgame perfect Nash equilibrium. Like, and what does that mean? Well, it means if you write out their utility functions and what the strategies the other player's doing, each is doing a best response. So,
right.
You know what I mean? Like he refused. He was like, no, what are you asking me? What does that mean? I don't know. I'm just telling you, this is what the definition of a subgame perfect Nash equilibrium is. These strategy profiles correspond to that. Let's go on. You know what I mean?
Right.
And so it was a similar thing.
So let me just comment on that. So on game theory, it's an interesting domain. There are all kinds of problems in porting claims about game theory into the real world. Because in order to get a lot of game theoretic results, you have to make assumptions that are totally unrealistic and could never hold. Now, if you make those unrealistic assumptions, you can do some cool math. Mm-hmm. And that's great for academics, right? But if you want to develop models that help explain the world, there's going to be some problems there. I want to give you one similar story. So I was at a private research group in Oakland. Mm-hmm. And we were talking about the philosophy of mathematics. And there was a young lady there who was getting either her master's or her PhD in math. And she said she was stumped by some particular problem for her thesis. And I forget what the theorem was that she was working with. And in a moment of insanity and creative craziness, she thought, okay, well, maybe the reason that I'm getting stuck here is that one of these proofs I was assuming was true is false. Like maybe there could be a math proof out there that is not actually solid and logically rigorous. Mm-hmm. And so she entertained that idea and like the next day solved the problem. She went in to speak with her thesis supervisor, mm-hmm. who promptly reprimanded her and said, well, who do you think you are? Mm-hmm. You're not in the academic hierarchy. You don't have enough gravitas to be able to claim what you're claiming. Didn't care about a proof. Didn't care that she might have just invalidated something that was supposedly believed to be true. She was, socially reprimanded for speaking out of line.
That's good. Let me give an example, because for the listeners, just us talking around, let me give a specific. So I don't know that this is the one that in the class when I asked the guy the question, if this is the one, but this is the type of thing that was going on. So if you have a prisoner's dilemma, but you play it many times over, but it's finite. The number of times you play a prisoner's dilemma is finite. And again, so folks who don't know, it's the kind of thing where if you both cooperate, then you both get a pretty high payoff. But if you or don't cooperate. If you do the selfish move while the other guy does the cooperative move, then you get a really high payoff and the other guy gets a really low one. And if you both do the selfish move, you both get a moderately low one. So it's like the worst outcome for you is if you do the cooperating one and the other guy screws you. The mediocre one is if you both do the selfish move. But the best outcome is if you both, the second best outcome is if you both cooperate. And then the best outcome is if you do the selfish move and the other guy doesn't. In a one-shot iteration of that. And so what's called the dominant strategy, no matter what the other person's doing, you should always do the selfish move. Whether he's doing the one that you always get higher. And so that's the thing to do. Then both players do it. So it seems odd that, you both end up with a lower payoff than if you both did the irrational move. And so in a one-shot setting, that seems kind of like counterintuitive. Okay. But what's really weird is if you could play that game 1 trillion times in a row and know that that's what we're going to do ahead of time. And the thing is, as long as it's finite, then you can use what's called backwards induction, and you go to the second last round, and you say, in the second last round, whatever has come, regardless of the history up to that point, should I cooperate with this guy? And the answer is no, because you can look ahead and in the final round, it's just going to be a one-shot prisoner's dilemma. And we all know the rational thing to do is for him to screw you. So in the last round, he's going to screw you. So given that he's going to do the worst thing possible to you in the last round anyway, for sure, in the second last round, there's no point in trying to bargain with, and try to do something to hope is hey, as we keep cooperating, maybe he'll reciprocate, right? That's kind of the intuition. And they say, no, you couldn't possibly, because in the second last round, you look ahead and know for sure he's screwing you in the last round. So there's no reason in being a nice guy in the second last round. And then you just use that logic. If that's true for n-1, it's true for n-2, because in the second, you know what I mean? And you go all the way back. And so okay, fair enough. And so that's a way you can prove that there does, the unique Nash equilibrium in this game is such, and it's even stronger conditions than that. Okay. What's weird though is you can say, what if in reality you go to play that game and you're absolutely certain that no, my opponent clearly is going to defect in every, do the selfish move in every single round because I can, prove it. And then what if he just keeps cooperating and you're doing your moves, you're doing the defection, so you're crushing it, but then it's weird because in other words, his behavior, you've already, the way you come up with what your optimal strategy is to make assumptions about his behavior that now he's showing you must have been wrong. Right. And it's a weird thing where their solution concepts can't incorporate that because you should never see that.
Okay. Two more examples, and then we have to talk about more of the concepts involved with infinity here. Okay, one example that's even more counterintuitive is the Banach-Tarsky paradox. To summarize, the idea is that you can have a sphere that you decompose into a finite number of parts. You can rearrange those parts in three-dimensional space such that you get a duplicate sphere the same size. Now, people will say this follows from the axiom of choice. You could say that way. We don't have to go into the technical details there. But it should be noted that part of the funny business is also the parts that you deconstruct the spheres into have an infinite number of points. And I'm like, okay, whenever infinity is cropping its head up here, we're going to result in logical paradoxes. There's an even stronger version, which is called the P in the sun paradox, which says, according to math, you decompose an object the size of a pea into a finite number of parts, reconstruct them into the object the size of the sun. I go, something seems a little bit fishy here. Okay, so that was example number one. It'll come back. Hang on. What was the thing you were talking about?
The finite repeated prisoner's dilemma. And if you see the other guy making moves that your logic told you would never see, why are you still committed to the strategy that was predicated on?
Yes. Okay. Great. Thank you. One more example. This comes from my book, Square One, The Foundations of Knowledge, where I talk about poker. And poker is an interesting example that illustrates some concepts in the philosophy of mathematics. So a dogmatic a priorist is going to tell you about the logic of poker. Where do they get their logic? Well, the mathematics of poker. There's 52 cards in a deck. There's a certain probability that you're going to get good hands versus bad hands, that your hand is better than the opponent's hand. So imagine we were playing a game of poker and you were a computer genius. You were like computational genius, knew 100% of the mathematics. It was like perfect information game insofar as you can get it in poker. And you played mathematically correct poker and you kept losing every hand. Now, somebody with the mindset that's too myopic is going to say, okay, well, this is just variance. Technically, you can have circumstances of bad variance where you just get, it's bad luck. So keep doing your strategy over and over and over, and eventually it will correct because that's the math. Now, somebody else might zoom out and say, well, hang on a second. Maybe we're playing with a stacked deck of cards. Maybe somebody's cheating.
Right.
Now, there's a baked-in assumption when you're doing your mathematical analysis of poker that might not actually hold in the real world. And what would the evidence of that be? Well, if you keep losing every hand and you're actually playing mathematically correct poker. Just like if the prisoner's dilemma, I don't really care what your math says. If it's in the real world, there's demonstrations that you made an assumption that's not holding.
One last thing too. Well, two things. So, Steve, don't let me forget to come back to the prisoner's dilemma thing. Okay. Let me to the poker. I may have even said this because you probably brought up what you just said the last time I interviewed you, because I know I brought this story, but it happened to me once. I was in high school. My brother's 6 years younger than me. So I was old enough that it wasn't wrong for me to take money from kids their age, put it that way. Or at least in my values.
It sounds like you're starting with the defense.
Right. So, but it comes back. It's funny. It's sort of like I was hoisted on my own petard. So I'm dealing blackjack and I have 2 decks and there's like 6 kids. And maybe I think I was in college and they were in high school. That's got to be what it was, because I wouldn't have taken money from kids in 5th grade. And so we're playing blackjack and they just kept winning.
Yeah.
And and they were playing poorly too. It wasn't that they just kept getting 21s. Like they were making ridiculous moves. And I was like, what the heck? And so, I'm down $40 or something. And so and I ran out of cash. And so what's the right thing to do? Well, no, this is I went to the ATM and got more money to be the house still, because in the long run, clearly I'm going to win all my money back, because not only do I have a slight advantage, these kids, I can tell they're not counting cards and they're not even playing basic strategy correctly. These kids are terrible. I mean, my brother was pretty good, but his friends weren't. And I sat there and I lost all the money from the ATM. And then every once in a while, I will still ask him, this is obviously decades ago at this way. And I'll say, come on, you guys were cheating that day, right? And he's like, no. Because I can't explain. So anyway, there was that. And then they were my decks too, by the way. So I was wondering, were they palming 3s and 4s? But I don't think that's what it was, because it was a kind of thing where they would have a 14 against. So they were hitting when they shouldn't have, and then getting, they'd have a 14 against my 3, and they would hit and get a 6. It was stuff like that. Right. That's what I'm saying. They were terrible. They were making ridiculous moves, and yet they were working out for them. Right. Okay, so then the other thing was the finite repeated. I just want to clarify in case people, they might say, sure, in game theory, and this is the kind of thing like a David Friedman or something would do, just in general in economics, say, we assume everybody's rational. Which for David Friedman is a much stronger thing than it means for Mises. Meaning they're supercomputers and they can do, just like if you're going to model a pool player, you assume he knows all the laws of physics and stuff if he's an expert, even though he doesn't. He approximates it, or it's as if he does. So he said, because there's all sorts of ways to model error, but we assume people correctly saw the thing just to get sort of a benchmark of if everyone behaved optimally. But the thing that's weird about what I'd said that the finally repeated prisoner's dilemma is, if the 2 players cooperate with each other for 16 billion of the rounds and then start defecting near the end, they will have both earned a far higher payout than if they both do the quote rational thing. Right. So that's what's weird about it, is that if you deviate from what the game theorists are telling you to do, in reality, you might end up making a lot more money than if you do what they tell you. This is obviously the right thing to do. So that's why it's weird.
We're never going to talk about infinity, Bob, because I got to jump off on that though. Okay. First of all, on game theory. So I'm gonna actually write something down so I don't forget. So let's start with the claim. Part of the reason I think this is important, these discussions about the relationship between math and reality, is because I have observed that the world of ideas is hierarchical. That is to say that some ideas themselves are just categorically more important than others. So when we're talking about the nature of logic, truths in that are logically rigorous can underpin a bunch of other truths. So there's a hierarchy there, and your beliefs about your who won the Super Bowl in 1967 don't matter as much as your beliefs about the nature of logic, for example. Okay, But there is also another hierarchy, which is the hierarchy of intellectuals.
Mm-hmm.
And in our current world, the peak of the hierarchy is the mathematicians. And some might say the physicists. Let's say mathematicians and the physicists. Who's the smartest? Who gets the final say? Who's the most prestigious? It's the math people, because what they're doing is like logically certain. You can't really disagree with the math because math speaks for itself. So there's a hierarchy here. So if there are a bunch of bad ideas in our intellectual hierarchies, that's going to cause downstream consequences. And I would say you'll appreciate this. For example, is the influence of mathematics in economics over the course of the 20th century, has that been a really great development? Or do you think that has... It's exactly. Now, there are abstraction errors that are made all the time when people are trying to apply math to economics. And that's the case with essentially every other discipline other than physics. And we could have like a discussion about the relationship between math and physics. So like there was a famous paper that was published, I forget when, it was called, it was something like, I'm not going to get the exact title. It's like on the inexplicable utility of mathematics in physics. Mm-hmm. And it was an argument that was his famous argument trying to say, wow, there's got to be truth in math because it's so practical. There was another paper published a couple days later, or a couple decades later. And it was something like on the inexplicable, impossibility of using math in biology.
Mm-hmm.
Because like in most areas, in 95% of the areas in biology, math is not going to help you very much. Now, you maybe when you're dealing with specific chemical interactions, if you're super zoomed in, maybe math is going to help you understand some things. But in general, we don't use math concepts to explain most phenomena in the world, in fact.
Mm-hmm.
Okay, so I wanted to say that. Other thing on the intellectual hierarchy, on game theory. So one of the most celebrated mathematicians of the 20th century is this guy, John von Neumann.
Yep.
Was genius, absolute genius, father of game theory. Okay, it should also be noted, Bob, that John von Neumann advised 2 sitting U.S. presidents to preemptively drop nuclear weapons on the Soviet Union. Why? Because his game theory predicted that nuclear war between the Soviet Union and the U.S. was inevitable. So think about the power of that argument. I am the smartest mathematician of the 20th century, and my mathematics is showing me that nuclear war is inevitable, therefore time to drop the preemptive nukes. I'm sorry, except von Neumann was wrong. There wasn't nuclear war between the US and the Soviet Union. So if you also see that there is an intellectual hierarchy that has implications in the real world, I think we need to re-examine very carefully some of the ideas that were come up with by mathematicians over the course of the last 140 years.
Yeah, that's a good one. Just to circle back to catch up on one thing you said, and then we probably should get into the topic that this was advertised as.
Yes.
So what we're going to do is postpone it for an arbitrarily long length as n goes to infinity, or as t goes to infinity. So you mentioned what is it, Barsky-Tanak paradox? Is that the name?
Tarsky paradox.
Tarsky.
Yeah.
Okay.
Yeah.
Have you read Richard Feynman's popular stuff?
Just the Surely You're Joking. That's the only thing.
I don't know if it was in that one or in the follow-up one. I forget. It was
where
like
he talks about the infinitely thin orange, that example. Where he was arguing with the mathematicians and he was like, there's no infinitely thin orange. What are you guys talking about?
Yeah.
He does talk about the Tarsky paradox in that book.
Right. So they were trying, like people in grad school or something. Yeah, we're trying to tell him you could take an orange and turn it into the sun.
Exactly.
And he said, no, you can't. And they said, and then they ended up invoking that theorem. And then he said, no, because that theorem requires to splice it up into an infinitely thin thing. And no, once you get down to, I don't know if it was quarks, whatever the constituent elements of matter were, that the physicists thought of at that point, he said, you can't get smaller than that. So no, that's where the theorem doesn't apply.
Right. And of course, and I guarantee you, the mathematician said, this unsophisticated rube, he doesn't understand the power of our mathematical formulas.
Okay, so it sounds like you did read about that, because I want to say that's right up your alley. So why don't we go into then, what are you just going around, going to the bathroom on everybody, Steve, here? Or what's your solution? Like, or are you saying arithmetic is wrong? Like we shouldn't just teach kids the times tables because, it's spooky math and we're going to end up using nuclear bombs if we teach people the times tables?
So I'm going to take the postmodern turn and say 2 + 2 = 5. There is no truth. Actually, it's the exact opposite of my position. So arithmetic is fine. In fact, large structures of math are fine, not all of them, because they can be rescued from these terrible ideas. So my claim is that all mathematics is fundamentally finite. In fact, I think the universe is finite. I think everything is finite. We can have an interesting discussion about that. It could get rather technical, but for all intents and purposes, all of our experiences are finite. Our minds seem to be finite. We can't conceive of an actual number of infinite anything. So I think you get as much conceptual horsepower as you need from the finitist position. That is to say, math works because calculations terminate. In fact, like, here's an interesting observation. Computers, when they're doing mathematics, they're not actually doing infinitary calculations. They're not actually adding infinite sums because they can't. If a computer engages in an infinitary process, you have to turn it off because your computer broke. It hangs. That's like the definition.
Mm-hmm.
So isn't it interesting then that we can still get some meaningful calculus out of our computers when they can't do infinitary calculations? I think the reason is because what the computers are doing is the real math. And then the theoretical academic mathematicians come up with a bunch of stories about infinities that don't actually port onto the real world.
Let me just, I think that's an important, I heard you make that in a different interview that I was prepping for this episode. Let me just make sure people get that. So what you're saying is people have this idea that, well, the math works, Steve, and you're saying, no, in practice, even supercomputers that you probably think are built on the principles that the higher mathematician gave you, saying, no, in practice, when your supercomputer like approximates pi, and notice that word approximate, it doesn't actually do an infinite number of calculations because that would take infinitely long. No matter how many calculations per second the latest supercomputer can do, it's a finite number. And you're saying what happens when they say it gets caught in an infinite loop. That's the kiss of death. That means, you got to break out of it because then your computer's just stuck forever and it doesn't give the answer if it's stuck in some procedure that it needs doing literally an infinite number of steps to reach the solution. That there has to be some way that it stops and then gives, this is what the answer is thus far.
So this should be a non-controversial claim.
Mm-hmm.
Every computation that has ever been performed and completed has been discrete in nature. That is, 100% of computation that has ever happened in any human mind or computer is discrete. Now, isn't that interesting that we have a dominant theory of mathematics, which is telling us that infinitary processes are fundamental, and yet nobody has actually undertaken one single infinitary process. That to me is like, okay, that's a red flag that clearly the theory and the practice seem to be broken here. And part of the reason, I think historically speaking, that finitism was not appreciated is because it's, in some respects, it's less elegant. It's a lot clunkier. The theory is prettier when you can smudge things in such a way that you get to say, this is actually continuous function and whatever. Things get very choppy and less maybe aesthetically pleasing when they're discrete. How did I start that? Man, I seem to have, this is the second time my train of thought has gone off the rails.
You said, well, I don't know if this helps, but you were just saying every calculation has been discrete thus far. Is that enough?
Yeah, I guess we can end it with that concept. Yeah, okay. Every calculation.
Have this train of thought be finite.
Yeah, exactly. That's a great example. There are several observations like this that I make as an outsider that lead me to suspect there are very deep fundamental problems with the theory. Here's what I was going to say was about history. So the clunkiness. So recent developments with computers and some a minority school of mathematicians have rescued a lot of smudgy continuous mathematics from the orthodox mathematicians, and brought it into the land of discrete computation. One of them is named Dr. Norman Weilberger, who I mentioned. I also had an interview with another guy, Dr. Doran Zeilberger, who is a hardcore finitist. He has a paper that's written. He called this is the funniest paper title ever. It's called "Real Analysis is a Degenerate Case of Discrete Analysis," something like that. Where he says actually what real analysis is, if you look under the hood at what's taking place, is it's all fundamentally discrete. So we are building out all kinds of amazing structures of mathematical knowledge with computers, with computation, when everything is concrete and finite. The theoreticians just haven't catched up yet.
Okay. incidentally, another example you can add to that, Steve, is the sort of like the deep work, or let's say the deepest, because maybe it's not deep in an absolute sense, that I do in economic theory is with capital and interest theory. And folks, I'll link to a recent chapter submission I gave. Per Byland is editing a volume, and it kind of sums up my career on this narrow topic. But it has to do, Steve, with like the mainstream economists being fundamentally confused about interest being equal to the marginal product of capital. And I realized this in grad school, there's a mistake they make, or it's rather they make an assumption that brushes everything under the rug. And I didn't realize this until listening to you do other interviews and talking about the the discrete versus the continuous stuff. But part of the problem is because they use calculus and they do everything with continuous flows, and the math is so elegant.
Yeah.
When they do it their way, and it's hard to see what's going on. And so when I give my counter examples, I always just do a discrete case, and it's crystal clear what's going on. In my case, when it's like t is t plus 1 or t plus 2, to see, and then the value of the machine changes from t1 to t2, and then you got to take that depreciation into account. And so we see that actually just because the machine's physically productive doesn't mean the owner necessarily earns an interest return. And when you do it with calculus, it gets hard to see that because the change in time shrinks to an infinitely small increment. And so, you know what I mean? So it turns into an instantaneous flow, and the idea of the machine's market value dropping over time because of depreciation or change in market conditions, and how that's something that can offset the rental flow from the productivity of the machine.
It's
harder to see that if it's just an infinitely, an instantaneous rate of change. Whereas if it's just a discrete, there's time 1 and then time 2,
Exactly.
Here's the general equation, and notice interest is not equal to the marginal product of capital in general, only in the special case when blah, 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 and then it reduces. So, okay, so you're, what that guy was saying with that paper is that in general, you can write out correct mathematics that's discrete, and then maybe if you take the limit as the steps shrink to 0, it turns into
nonsense. So let me give you an example. So I want to say one point here. You mentioned the concept of instantaneous rate of change. Okay, that's like a central concept in calculus.
Right.
That concept is kind of weird itself. What does that mean? An instantaneous rate of change. When I think of change, I think of at least two states. So the idea is with the notion of the instantaneous rate of change is that somehow when you're trying to you're trying to do calculus and you're finding, let's say, the area underneath the curve, and you the way you're doing it is by building little strips of rectangles. Okay, the idea is, well, the theory is you make the rectangle infinitely thin, and then you find the exact instantaneous rate of change. I actually don't think that makes sense. I think the notion of change is one that requires at least two temporal units.
Right.
So,
okay.
So let me give you an example that I really like that helps illustrate why things go off the rails when you start talking about instantaneous rate of change, taking the limit, the point at infinity. This is an intuitive example. Okay, so I can say, imagine a circle whose radius is infinite. I can say those words. I might even think I know what I'm talking about. But consider that concept and then zoom in on the edge of that circle. And the question is this: is there a curvature to the edge of a circle whose radius is infinite? And if there is some curvature, because it's a circle, then I'm saying you're actually dealing with a finite circle. You just follow the curvature, whatever the curvature is, literally whatever it is, it's non-zero. Follow the curvature around, you have a finite circle. But if that means the curvature of the infinite circle is actually 0, you're dealing with a straight line. You're not dealing with a circle. So it is precisely at the point of infinity where the logic breaks, the logic of calculus breaks. It doesn't make any sense anymore. I can say, imagine a circle of arbitrary length. Okay, that's fine.
Right.
Or if we're talking about infinite series, I can say, imagine this series goes on for 500 trillion years. No problem. But when you start saying it is an infinite series, and then you're going to extract a meaningful value from the end of that infinite series. I go, that doesn't make any sense. You've broken the logic of your mathematical formula.
Right. And again, just for people at home to drive home what Steve's saying, you're not merely saying, Steve, that, it's unrealistic. Your point is, no, it leads to a contradiction.
Yes.
That if you actually tried to logically think through the implications of a circle of infinite radius, its edge necessarily could have zero curvature, because if it had any finite curvature, you could back out.
You could create it.
Well, then what's the finite radius? Like, as some function of that curvature. And that contradicts our initial assumption that there was infinite radius. And then your point is, then it's not a circle. So it's not just that, it would be unrealistic. Like in the real world, we'd never see an infinitely big circle, but we could think about it. You're saying, no, you can't think about it.
You can't think about it. You can think that you're thinking about it, but you can't actually think it through.
You would end up with a contradiction.
There's a historical precedent here. So Newton is given a lot of credit for calculus. He's the co-discoverer of calculus. I don't think actually that's true. It might have been an Indian mathematician who was traveling Europe prior to the supposed co-discovery of calculus, but put that point aside. In Newtonian calculus, there's this concept of the fluxion, which in our language we would call the infinitesimal. And in Newtonian calculus, he treats the infinitesimal sometimes as zero and sometimes as non-zero. Because if you treat it as zero, you can erase it out of your formula. But sometimes you need it, so it's got to be non-zero. George Berkeley, the famous philosopher, came along later and wrote a book called The Analyst, where he said, it takes less faith to believe in the God of the Bible than the mathematicians, because this is Newton, in his powerful structure of calculus, makes a logical contradiction where he says, sometimes it's zero, sometimes it's non-zero. And he has this quip where he says, the fluxion, it's like the ghost of a departed quantity. Or something. So it's like, it's this ephemeral thing. Sometimes it's this, sometimes
Newton
it's that.
says that, or the guy who's making fun of it?
No, Berkeley says this afterwards, criticizing Newton.
Right.
And as the story goes, mathematicians at the time said, no, this isn't true. Berkeley just doesn't understand the sophistication of mathematics. Then eventually, it'd be 150 years later, somebody cleaned up the logic a little bit more in Newtonian calculus. And then the mathematician said, okay, yeah, Berkeley was right, but now we have the final, perfect, beautiful calculus.
Yeah. Okay, why don't we try this, Steve, just for the listener who is somewhat acquainted with this stuff, took calculus and said, wait a minute. What happens then to the notion of velocity, right? So, and you could say, you're driving in your car and you're at this one place, and then an hour later, you're 50 miles away. So on average, you were traveling 50 miles an hour. But we all know you could have been going really fast for one stretch and then been stuck in bumper to bumper track for the rest. So it's not that you were going the same velocity throughout the whole hour, just on average you were. And then you could say, you could see, okay, what if in the first half hour I went 20 miles? And then, and then you keep, and so just say, what does it mean when we look at our speedometer? And it says right now we're going 45 miles per hour.
Yeah.
Yes, one implication of that is if we maintain this velocity for 1 hour, we'd be 40 miles further down the road. But that's not necessary because we might change. So to even talk about what do we mean when we say what's the velocity, isn't that necessarily meaning, well, it's the limit if you kept doing that as the delta t shrinks to zero?
So I think velocity is another concept that presupposes temporal progression. So velocity is a way of talking about how states of a system change over time. So it's not hard for me to understand the notion of velocity at all within the finitist framework. It's like, or motion for that matter. There's a really fundamental question that Zeno brought up with Zeno's paradox is, right? How is motion possible at all if, in order for Achilles to finish the race, he has to transverse over an infinite series of points? Now, this is another interesting historical example, if you'll humor me here. So Zeno, I agree with Zeno's logic here. So Zeno says, in order for Achilles to finish the race, he has to go, before he finishes the race, he has to go halfway to his destination. Okay, so he's at the halfway point. But in order to go from the halfway point to the final destination, he has to go through another halfway point. And then the quarter point, and then the 8th point, and the 16th, and so on. And so Zeno said, well, if space is infinitely divisible, that would mean that there's an infinite number of points that Achilles has to cross. You cannot cross all of an infinity. Therefore, Zeno said, motion is impossible. And because he thought space was infinitely divisible. So I like his logic, but he's got an incorrect assumption, which is that space is infinitely divisible. In fact, Zeno's paradoxes evaporate into smoke if space is discrete. If there's a fundamental base unit of physical space, at some point, Zeno is at the last unit of space before the finish line, and then he crosses it. All the paradoxes sort of disappear.
And it's interesting because that's somewhat analogous to the way Feynman evaded the rhetorical trap that those people in grad school were springing on him.
Yeah.
To just say, no, you can't turn an orange into the sun or into a thing with the volume of the sun because at some point, you can't divide it into smaller components.
Yes. So, and there's a practical question here, which is good for the physicist and good on Feynman for saying that. I would actually make a stronger claim, which is that it's logically necessary. So I would say to the extent that motion is possible, it must be the case that space is not infinitely divisible. I'm not even sure the concept of infinitely divisible space makes sense at the conceptual level. That's a little bit harder an argument to make.
So I think the standard, what I've seen, like in a philosophy book or something, so I don't know if this is the consensus, but what I've seen is the sort of glib, Zeno raised this ostensible paradox that how could somebody, finish a race because, to cover the distance, you'd have to first cover half of it and so on. And he said, but the solution, of course, is that you can perform an infinite number of steps in a finite period of time.
Yeah, but they say calculus solves this. Like the calculus solves this logical puzzle.
Yeah, so to this, he didn't use the word calculus, but he just, like his straightforward resolution was to say, which I agree with, if this were correct, then it would solve it, is to say, you can perform an infinite number of steps in a finite period of time. And then he just moved on. And that's really what you're saying. Oh, no. Says who? And you had a funny line in an interview I saw you where you said the way mathematicians solve that is they use a ...
Yeah, I call them magic ellipses. Or all sorts of mathematical constructions and formulas that are just trivially thrown out there as infinite series are hidden behind this ... So I said in this interview, do you understand the magnitude of what is being claimed behind these magic ellipses? Like imagine you've got that series a half plus a fourth plus an eighth plus a 16 ... and it continues ad infinitum. Okay, that would mean that you could imagine the entire universe was a computer dedicated to the generation of this series. Every bit. Like what you and I are doing in God's plan is actually just calculating this series. Like the sun, it's all part of a gigantic computer that is meant to calculate this one particular series. The entire universe could be trying to generate this series for 500 trillion years. And they still would have essentially generated none of the series.
Right.
And that's how much computation the mathematicians claim they're performing when they do the ... I come along as an outsider and I say, no, I think something else is going on here.
Right. And again, just for folks who say, oh, come on, Steve, because I know people would be tempted to say, yeah, we get what you're saying, Steve, as an outsider, and it seems weird, but come on, we know it works, right? And that's why I want to say, well, no, that's what this Riemann's rearrangement theorem to me showed. What would it look like if it didn't work?
Yeah.
Wouldn't it do things like saying, oh, if you have an infinitely long series under certain conditions, it's got to be conditionally or convergent, blah, blah, blah. You can rearrange the terms and get whatever answer you want. And isn't that the way things would look if Steve is right to say something's fishy with that move rhetorically? I forgot to quote this. The thing I looked up to get up to speed on what this Riemann's rearrangement theorem was, it's by Stuart Galliner, and it was written in 1987. And he's motivating it, and he has this thing. So it's a quote from this guy, Niels Hendrik Abel, wrote in a letter to a friend in 1826. Divergent series are the invention of the devil. By using them, one may draw any conclusion he pleases, and that is why these series have produced so many fallacies and so many paradoxes.
Yep.
Okay, so again, to be clear, it's the thing, Riemann's theorem is not about a divergent series, it's about a conditionally convergent one that's composed of two different divergent series that are added together. But still, the mathematicians themselves, they knew something's screwy with these things, and that guy brought up the devil. And you could say, oh, he was just being colorful, but you actually do think that, no, this really is the source of
the devil
serious,
himself.
Human suffering.
Absolutely. And I'm not alone in this. So I ventured into this land solo. I thought for a little time before I had investigated the history more, I was like, I have really tried to make sense of claims of infinite totalities and completed infinities. And I just can't get it.
Right.
So I thought for a while, well, there are limitations of knowledge. Maybe this just means I am actually stupid. What a delightful conclusion to come to.
Right.
I've been trying to solve these puzzles for, I don't know, a decade now, and I still can't. So you've seen the limitation of what I'm capable of. Then, fortunately, I got into more of the history of mathematics. I'm like, oh, there's a rich history of minority schools of people criticizing these ideas. Cantor. There's a quote from Wittgenstein, the philosopher, who considered he thought of his work. He thought that his work in the philosophy of mathematics was the most important work that he had done. And I think it was him that said set theory is a disease.
Wait, this is Wittgenstein said this?
I believe this is Wittgenstein. Okay. That set theory is a disease that one has to be cured from.
Mm-hmm.
Kronecker was another famous mathematician of the 20th century who rejected the notion of the infinite totality. Brouwer was another one. Here's some relief for people who are getting anxious about the idea of rejecting infinities. This guy that I brought up a couple of times, Norman Weilberger, he has developed a theory of trigonometry that he calls rational trigonometry that does not deal with transcendental functions at all. No sine, cosine, tangent. Everything in rational trigonometry is like rational numbers. No appeals to infinity, no infinitesimal expansion, none of that. So he has found a way to rescue trigonometry from concepts that are conceptually confused. And I have the suspicion, if that's possible in trigonometry, it's literally possible in, let's say 90%. Maybe that's an overestimation. A lot of the math ideas that we take for granted and we think give us truth, I think they can be reformulated in a way that suddenly make more sense and are actually more precise. Like if you don't allow for infinite decimal expansion in your mathematical structures, you're actually going to end up with a more precise mathematical theory because you don't have to do approximations. Get rid of the notion of truncating infinite series arbitrarily. Everything fundamentally is discrete. Suddenly you regain total precision.
Yeah, and like I say, I just keep coming back to my work on capital theory and economics that it was crystal clear logically when I was using discrete examples of stuff what it was, but it was messy. It was clunky. Like the term, you had all these terms floating around or whatever. Whereas, if you just let stuff shrink to zero, then the stuff it reduces to this nice thing. You just put the little partial derivative sign in front of it, and it's nice. And like I say, so by the way, I think I could still have made my points even in the continuous case. Like it's not that I'm saying Samuelson was right with the continuous case. It's just it was so obvious when I did it in the discrete setting that what he was doing made no sense. And also, the nice thing was to say, clearly, if something is true in a discrete case, if something doesn't work with the discrete case, but only works in the continuous case, and you're talking about economics and what's the value of a machine and stuff, I think most people would at that point say, okay, let's go with the guy who's showing in discrete, because in the real world, where it's interesting that within math, it's like, no, if you show me something that's not true for any finite iteration, but if I let it and go to infinity, then it is true. They seem to think that's where all the action is, and the thing that we all agree could never happen in reality.
Exactly. Yes. And this I think, so I've heard somebody else say this. I forget who it was. They said, mathematics is the only discipline that has not been influenced by like Enlightenment thinking, but they're still stuck as scholastics, thinking that they have built these a priori, absolutely rigid structures of knowledge that aren't going to be revised, and then they do like logical deduction from there. And we not to revisit the a priorism discussion, but I think there's some truth in the notion that math has not really been updated. There is we tell this story of mathematics that I just don't think is correct. That the universe is written in mathematics. Mathematics is the language of God. That if you want to know the fundamental principles of anything, ultimately, there's going to be some mathematical formula that expresses it. I just don't think that's true. Now, not only do I not think that's true at the conceptual level, when I actually look at the world that I inhabit, it's certainly not true right now. It's just not. You don't apply mathematical calculations in your social relationships. You don't. I mean, you can in economics, but in practice, you're probably not going to do that much advanced mathematics and economic calculations that involve actualized infinities, that type of thing. That's like just boring old arithmetic. in the domains of life that we actually inhabit, I don't think we're anywhere near getting to any kind of general mathematical truth, like about human behavior. Like
Right.
show me the mathematical formula which gives me concrete predictions about human behavior in the real world. Are we anywhere close to that, like in any domain? Now, maybe in the aggregate, maybe we can come up with useful statistics. But in terms of like the predictive power that you might get in physics when you shoot a cannonball and you're like tracking its trajectory, that gives you some amount of repeatable precision. Is there anything like that in the human domain? I don't think there is.
That's all true, but I'm concerned if you say that and put too much weight, then people are going to think you're merely saying, wow, humans are really complicated and we don't yet have the right mathematical formula to predict human behavior. But you're saying something a lot more fundamental than just that.
Well, I have to keep it as a logical possibility that there are actually such universal formulas, and like God is sitting on his throne observing the world, and it's simply every single state of the universe is an output of the previous state, and it's all inputs and outputs.
Hang on.
Possible. Yeah.
Why isn't? I mean, I would have. So here, see, I couldn't predict your behavior. I would have thought your position would be, oh yeah, math is very useful, and since the universe itself is discrete, and I'm not merely saying that because of observation, but because if I think it through, how could it be anything but discrete?
Yeah.
Then discrete mathematics presumably describes the universe perfectly, or at least I'm open to that possibility. And so it's not surprising, since the smallest increment of space and time is very small relative to our everyday experience, that calculus ended up being pretty useful, just like Newtonian mechanics was useful until we started talking about really massive things or things close to the speed of light. But in terms of our everyday, so couldn't it be that, the language of the universe is math, but it's a discrete math?
I'm open to the possibility. I would just say at our present state, I find it absolutely preposterous. It's like, was it Pascal it was Laplace, Laplace's demon. The idea that, if there was somebody that, or a demon that knew that had all the information about the current state of the universe, they could predict future states.
Mm-hmm.
Totally. Yeah. I am open to that idea. But imagine somebody said, this is logically possible, and here's the mathematics for it. Here I'm going to present you in 2022 with the mathematics of predicting all future states of the universe. I feel like you're not even close. You're like, maybe in 500 million years, you can start talking about that. But in the foreseeable future, it just seems like an utterly preposterous proposition.
Well, I think partly the reason that I'm okay with that is because anything we did in practice would just involve a subset of the universe, like whether it was a computer or, you know what I'm saying? And so how could it be that like a portion of the machine could explain the behavior of the whole machine?
So imagine that there are repeating patterns such that over here in this quadrant of the universe, we have discovered that, it's actually over here and it's over here. And there's some logical reason why the patterns have to be that way. And so they extrapolate to the totality of the universe or something.
Okay, fair enough.
Yeah.
But I'm just saying I could see how like you could logically think through that maybe God is looking down on the physical universe, that he created it, but it's distinct from him, that he could foresee the future with certainty.
Right.
And such. Okay. Are you okay if we go like 10 more minutes?
Yep, happy to.
All right.
It's like my favorite conversation ever, Bob, so we can go as long as you want.
So let's see. Why don't you very quickly tell the thing I heard you say, and I didn't know this. You said that actually Schrödinger, with his Schrödinger's cat, was doing that as a reductio ad absurdum, and then now it's been flipped?
Yes. Oh, okay, Bob. So you got to help me coin a term. This keeps coming up, and I don't have a term for it yet. It's where somebody accepts an argumentum ad absurdum. Like you lead them. So in other words, if your idea was true, it would lead to an absurdity, and then they go, "Yep,
yeah."
I don't have a term.
You call it Krugmanism because he did that with people. So we just thought aliens were going to invade, and he goes, yeah. In other words, it's
okay.
I'm botching it. It's a little bit glib, but people like saying to John Maynard Keynes, so if we just paid people to dig holes up and then fill them back up, that would be good for the economy. Yes. Yep. If you're stuck in a liquidity trap, yes. Whereas you think that you're zinging them and they just bite the bullet and say, okay, yep.
So please help me coin that because that keeps coming up. So going with Schrödinger. So the Copenhagen interpretation leads to what seem to be paradoxes, where you end up saying you can't actually make claims about reality in some state outside of measurement, the measurement of it. And the history of this, tracking this idea is very interesting we can go into specifics if you want. But anyway, this guy Schrodinger, famous physicist of the 20th century, essentially said, listen, if that were true, it would lead to a circumstance where you have the cat in the box. Prior to measurement, the cat is alive and dead at the same time. And then you open the box and then reality takes a state. As to demonstrate, you got some conceptual problems here. If the cat is dead and alive, that doesn't make any sense. And through the tragedy of academic intellectual progression, somehow we live in a world now where people appeal to the concept of Schrodinger's cat to show the magic and mystery of quantum mechanics. And they go, oh my gosh, the world is wild and crazy like Schrodinger's cat. And I'm sure he's rolling in his grave every time that happens.
And he's half alive and half dead in the grave until we look. There's something, do you know what the EPR paradox is? Mm-hmm. Okay, yes. So that's similar, except I think Einstein was famous enough that people knew they had proposed it as a silly thing. And then later people were invoking and say, yeah, actually they were right, even though they thought they were zinging quantum theory.
So Einstein's an interesting example. Seemed to be a clear thinker. From my understanding, he wrote a letter, I think it was actually to Schrodinger, where he was talking about the notion of continuous space, because questions about is space discrete or continuous came up back then as well. And he said something like, my theory of general relativity, I'm putting words in his mouth, presupposes the idea of continuous space, but I'm open to the notion that this is a castle in the sky. That's Einstein's words. Einstein considers his own theories potentially a castle in the sky, and it might be the case that space is discrete, and then we have to reformulate things. Good on Einstein for saying that. That's a sign of genuine intelligence. You can be like, look, it's a theory, I might be wrong. So if you follow the storytelling of physics, people go, Einstein was great, and then the poor man drifted into senility. Like he rejected the beautiful notions that we've learned on quantum mechanics. He just couldn't accept how counterintuitive quantum mechanics is, and he became a crank, just denying to the day of his death the truth of quantum mechanics. I'm thinking, no, I don't actually think, I don't think that's correct. I think insofar as Einstein refused to accept various parts of the Copenhagen interpretation, he was justified in doing so.
Right.
And again, there are lineages of thinkers, both in math who are finitists and in physics, who have said, from the beginning, these fundamental concepts are incorrect. At sort of the base level, we're using concepts that don't check out and eventually lead to paradoxes.
Right. And so what? Well, okay, why don't we back up a second then? So am I right in thinking it's not merely that you reject completed infinities in mathematics, but you also don't like imaginary numbers and you don't like irrational numbers?
So I like the explanation that was given of imaginary numbers by their inventor. I forget what his name was, some Italian mathematician. And he said, these are useful fictions. Mm-hmm. The idea of the square root of -1. Mm-hmm. He was like, this concept doesn't make sense. I can't make sense of it. But if we just overlook that for a second, look, it solves a bunch of mathematical problems. Right. You invoke the notion of imaginary numbers. So I think that's fine. I think imaginary numbers can be very useful. I think actually there's a way to make imaginary numbers sort of make intuitive sense. There's some interesting videos of this online where they're talking about like, it's actually applicable for rotation in a particular dimension. It's like this concept comes up and it's really useful. So it's great that you can get utility out of it. I have no doubt that there is a way to rescue the concept of imaginary numbers within a paradigm that says, we're using a new concept in place of imaginary numbers. That isn't actually the square root of -1. Like that doesn't make any sense. But also, Weilberger is a guy who is developing like rational mathematics without real numbers. Like I said, transcendental functions. So you don't need real numbers. The theory of real numbers has problems with it because you're going to bump into problems of infinity. So, yeah, a lot of the formal theory around modern math, I think, is conceptually imprecise and unnecessary. And it's just going to take a little bit of time to rescue the good parts from the bad.
Okay, let me why don't we end with this one then? Just a few minutes here. So what's interesting, let me ask a real quick one, Steve, just to get your reaction, and then I'll end with the final question I had for you. Are you saying you wish these people hadn't published their results on this stuff? Or are you saying they should have, just because, hey, look at this, just like, hey, what if General Zod, actually flew into a black hole? What would happen? And it's worth thinking through, like, given the axioms of what the Superman comics had established, what would be the outcome?
Right.
It can be fun little things like that, or you're saying, no, they just shouldn't even have run through the implications of these assumptions.
So I'm definitely not in a position to say with confidence. This is a really difficult question here about theory generation and whether or not it's good to discard sloppy concepts from the get-go, or it's a good idea to allow them and just see what follows. Let me just make this. My own thought comes from the following observation. Academics and intellectuals are extremely hierarchical. Very few of them are thinking, especially in the domain of mathematics. It's math proof after math proof, and you don't re-examine the proof that you've assumed is true. So like you're just building out these logical structures, and that makes me very skeptical that that's the right approach. I also think that when you look in the history of ideas, you have, to use probably a loaded word here, you have like persecution of dissidents. This happened in physics as well. In various cases, people that were dissidents, like John Bell, for example, had to move to Brazil because, the claim is he was a secret commie, and so people were, the government was going to persecute him. In reality, when I look at it, it's just John Bell had some cojones and said, actually, we can reformulate this. And actually, I'm not going to go into that story, but John von Neumann made a proof appealing to math that was wrong. John Bell pointed it out. People didn't like that because von Neumann was supposedly this genius. So I see the same thing in mathematics as well. Like if you dive into this area, Bob, please do. You're going to find so much vitriol directed at heretical mathematicians. It's shocking. I've said this multiple times and people don't believe me, where the most dogmatic people I have observed in my entire life has been mathematicians. Over the past decade, I've looked into the claims that have been made, the utter arrogance of the mathematicians saying we've solved the puzzle once and for all. These are the final truths. Don't question them. If you don't understand them, it's because you're stupid. And they're just absolutely immovable in their positions. They can't. A sign of bad thinking is that they literally cannot conceive that they could be wrong because of the nature of math and like a priori reasoning. They go, "What do you mean?" It's like it's a mathematical proof. When i.e., that means it is true. Like so. Anyway, that's a long way of saying I think that there has been serious persecution of dissident ideas in every domain, math and physics included. And I think going forward, we intellectuals have technology like the internet that is going to help them produce and preserve better structures of knowledge than we've had prior to the internet. I think that heretics going forward are going to have a much better chance. I'm not sure if the world would be better off if these people didn't have their ideas published and people dogmatically believe were necessarily true. I can't make that claim. I can just say going forward, I expect there will be less successful purging of dissidents in the future.
Okay, good. All right, the last thing I wanted to ask you, and you can, isn't it, I can imagine, well, and I'm wondering this too, with other areas where stuff is sloppy, and like here, with Freud, he had some good insights, but then he brought in this crazy thing, and then look what happened, or economics, so forth, all these things. To me, it's not like there was all this beauty that got generated from it, but alas, there was also this horror that was spawned. It just seemed like it was just nonsense, and it just kept accumulating.
Yeah.
Whereas in math, like for example, there's Euler's formula, and Gene Callahan on his blog one time had a post called "A Short Proof of God's Existence," and he just has E raised to the power of I times pi plus 1 equals 0. And he was saying that that contains 5 of the most elementary things from math from different domains. Like there's no reason a priori, you would have expected E and I and pi to have to come together like that. And he's quoting it. Feynman apparently said of that, he called it that equation our jewel, and said it's one of the most remarkable, almost astounding formulas in all of mathematics.
Yeah.
So I'm saying you wouldn't have expected, if this is all just crazy stuff, and that one doesn't involve, it involves, two irrational numbers, and an imaginary one. Why do you see these things? You know what I mean? Like, it doesn't seem like it's remarkably elegant if it's really just a bunch of nonsense.
So I could say a couple of things on that. First of all, we could make the same claim about Newtonian physics. Newtonian physics has a certain elegance and to it. And in fact, some people said it was a priori true. They thought through the concepts of Newtonian physics, and they thought, this is too elegant to possibly not be the truth of the universe. Mm-hmm. And then, you wait a little bit of time, and let's say that Newton was wrong. Not going to make a strong claim in physics here, but let's say you agree with the story of what has happened with modern physics. And we go, okay, actually, Newton is a good approximation, but there's a truer physics, and it's a hell of a lot messier. Okay, so I would say there would be a counterexample to the notion that your pretty formulas definitely poured onto the world. I have another one that I use, which is the Ptolemaic model of the solar system. If you look at the Ptolemaic model of the solar system, is the idea that the Earth is in the center of the solar system, everything revolves around the Earth. If you look at a map of the Ptolemaic model, it's beautiful. You have the beautiful Earth in the center, and you have all of these lines that it looks like a flower of all the celestial bodies rotating around the center. In fact, you could use that model of the universe to successfully navigate from Europe to the continent of North America just by looking at the stars with this model. Wow, it even has predictive power.
Right.
And it was completely wrong. And then you look at what our claims are about the current ordering of the solar system, and it's much messier. It's like nested ellipses that are sort of all over the place, and then like the sun is spiraling itself through space. It's a hell of a lot messier. Okay, so there's another example where the messy just turns out to be more correct. However, I could say that that maybe there is truth in Euler's formulas, but it's phrased in the wrong language. So if you're a finitist, you might be able to rescue the concept of E and I and pi, no problem. And so maybe there can be truths communicated in that formula. It just needs to be put into a language that makes more sense. And maybe the discrete reformulation of Euler's formula is going to be even more beautiful for all I know.
Right.
Yeah.
Okay. Well, that's good. Well, you've got your homework set out for you. That's what you need to do.
Yeah, right.
All right. Well, my guest today, folks, has been Steve Patterson. Steve, where can people go if they want to see more of this heresy? So steve-patterson.com is my website. I've got a couple of books. One of them is outdated. It's on Bitcoin. The other is called Square One, The Foundations of Knowledge, and it goes into what I think are the true foundations of knowledge and truth, the claim that logic and existence are inseparable. I try to defend that proposition. And then, I have a YouTube channel, youtube.com/Steve Patterson, where I have various series where I've interviewed people on this topic and 100 others. And Bob, I want to say too, it might be a little bit earlier to announce this, but either by the end of this year or sometime next year, I'm going to make my own institute. I'm going to be doing research because I think we're actually in a dark age right now. And I think there's a lot of evidence, like in every domain, there are critical problems that have to be solved. And I've reached a point where I'm going to need help. I am actually not interested in the details of math, like the actual formulas and numbers. I'm like, whatever. I care about the philosophy of it. I don't really care that much. So other people definitely, if you like math and you want to be an ambitious mathematician and try to maybe help us reformulate the foundations of math, contact me. Let's get together. I'm going to try to fix problems that I see. Let's say next year. I would say, so we're going to reinvent the wheel, but no, we're actually going to reinvent a polygon with very many sides that looks like a circle. Yeah, exactly. No such thing as preposterous notions of a circle. Come on. Okay, well, great. So that's all good stuff, and maybe I will. I'm going to work on that Euler's reformulation. Okay,
Nice.
So folks, for all
Okay.
the links to everything Steve said and some of the stuff we talked about, go to bobmurphyshow.com/229. My guest has been Steve Patterson. Steve, thanks again for joining us.
Thanks, Bob. Really my pleasure.
You've just experienced another episode of The Bob Murphy Show, the podcast promoting free markets, free minds, and grateful souls. For more information and to subscribe to this podcast, visit bobmurphyshow.com.